Hey, what's up guys? Welcome back. In this video, let us take a look at what are binary search trees. A binary search tree is a binary tree in which every node in the left subtree is less than the root node and every node in the right subtree is greater than the root node. And this is how a typical binary search tree looks like. Now let us take a look at the terminologies. So here is the binary search tree, and if you take a look at this binary search tree, you can see there is a root node called 16 and it has two children, left child and right child. Left child is 13 and the right child is 21. And also here we can see there are few leaf nodes. 11, 15, 19 and 26 are all leaf nodes because they don't have any children. And this portion of this portion of this binary search tree is called left subtree. Okay, and this portion of this binary search tree is called right subtree. Okay, and binary search tree is going to have these methods: insert, hide, search, display, and delete method. Now let us take a look at each of these methods in depth. Okay, so let's say we want to add a node or insert a node to this binary search tree. Let's say we want to insert a node called 17. Okay, so the first step is to compare this node with the root node, which is 16. Okay, so when we compare 17 with 16, 17 is greater than this root node, then we know that this node is going to belong to the right subtree of this binary search tree. Okay, so we will come this side, and now we will again compare this 17 with this node, that is 21. Since 17 is less than 21, it's gonna go here. Okay, and now we will again compare 17 with 19. Since 17 is less than 19, it's gonna go to the left side of this node 19 node. Okay, and now let's see if you want to insert a value like 10. So let's say 10. So we'll compare 10 with 16, which is smaller. We are going to go on the left side and we will compare 10 with 13. So 10 is smaller. Again, we will go to the left side, and now we will compare 10 with 11. So 10 is smaller. So we'll again go to the left side. Okay. So we will add it to this binary search tree. Okay. So that is how the insert method works. Now let us take a look at the height. So we calculate height based on the number of levels present in the binary search tree. So this level is called zeroth level. So zeroth level, and this level is called first level, and this level is called second level. Okay, and the height is basically calculated by the last level. So the height of this binary search tree is equal to 2. Okay, if this binary search tree had few values like this, okay, then you can also add few nodes here, then this level is going to be the third level and the height would have been 3. Okay, so that is how the height method works. Now let us take a look at search now. So let's say we want to find whether the node 10 is present inside this uh, binary search tree. So we'll compare 10 with 16. 10 is smaller, so we will traverse this route. So let me erase these extra nodes. Okay, so will traverse to the left side, and we will again compare 10 with 13. So 10 is smaller, so we will again travel to the left side, and we will compare 10 with 11, so 10 is smaller, so we have to travel on the left side, but there are no nodes present, so now we can return false because we have reached to the end of the binary search tree and we couldn't find this node 10. That's why we return false. Now let's say we want to find whether the node 19 is present inside this binary search tree. Okay, so what we are going to do is we'll compare 19 with 16. Since 19 is greater, we will travel to the right side now. And now we will compare 19 with 21. So 19 is smaller, so we will traverse to the left side of this node 21. Okay, and now we will compare 19 with 19. So since we found this 19 in the binary search tree, we will return true. Okay, so this is how the search method works. Okay, we already saw insert and hide. Now let's take a look at the display. Display basically it is going to display the binary search tree, and there are three main three main traversal methods. So the first method is called preorder, and the second method is called inorder, and the third method is called postorder. Okay, so now let us take a look at these traversal method one by one. So let me get rid of this binary search tree. Okay, so there are mainly three traversal methods. So I'm going to write three traversal methods. So the first method is called preorder, preorder traversal, and the second method is called inorder traversal, inorder traversal, and the third method is called postorder traversal. Okay, postorder traversal. All right, now let us take a look at these traversal methods one by one. So the first traversal method is preorder. So in preorder, what we do is we first visit the parent node. So let me write preorder here. So here we first visit the parent node, parent, and then we visit the left node, left, and then we visit the right node. Okay, so here is the binary tree. Let me quickly draw that here as well. So it has these nodes and 16, 13, 21. So this is 16, this is 13, this is 21, and 11, 15, 19, 26. Okay, so these are the nodes. In pre-order traversal, we first visit the parent node, then we visit the left node, and then we visit the right node. So the first things first, what I'm going to do is I'm going to visit the parent node. So I'm going to write 16 here, and then I'm going to visit the left node, that is 13. Since this node 13 has children, I'm again going to visit the left node. So I'm going to write 11, and then it says right node, so I'm going to write 15. Okay, and after 15 I have to go to the right subtree. So the first node which I have to visit is 21, which is going to be the parent node, so I'm going to write 21, and then left node, so which is going to be 19, and then I'm going to visit 26. Okay, so this is how the pre-order traversal works. Okay, so we visit parent, okay, and then left, and then right, like that, and then we visit parent, then left, and then right. Okay, we traverse in that order. And now we will see the in order traversal. So I'm going to write it here. In order traversal. Okay, so we'll consider the same binary search tree. Okay, so in order traversal, what we do is we first visit the left node and then parent node, and then right node. Okay, so if we consider this same binary search tree, we first need to visit the left node. So I'm going to visit 16, 13, and 11 is the last node. So I'm going to visit that 11, and then I'm going to visit its parent. Its parent is going to be 13. Okay, so I'm going to visit 13, and then what I'm going to visit is it's going to be the right node, which is 15. Okay, and the parent node of 13 is going to be 16, so we will visit that now. So 16, and then we will come to the right subtree and we will go to 21, but 21 is going to be the parent node, so I have to visit the left node. So I will write 19 and then 21 and then 26. Okay, so the best part about in-order traversal is it is going to give us the values in sorted order. Here we can see we have 11, 13, 15, 16, 19, 20, 21, and 26. All these numbers are in sorted order. Okay, and the final uh, traversal method is post order. Okay, so I'm going to write it here, post order, post order traversal. Okay, in post order traversal, what we do is we first visit left node and then we visit right node and then we visit parent node. Okay, so here in this binary search tree, we will move to the left subtree and we will go down, and the first node which we are going to visit is going to be the left, which is going to be 11, and then we will visit the right node. So right node is 15, and then we will visit the parent of these two children. So the parent is 13. Okay, so now what we do is we will directly come to the right subtree and we will traverse from a 21 node to the left side. So left side, the left child is 19, and we will visit the right child, which is 26, and then we will visit 21, and finally we will visit the root node. Okay, so this is how the post order traversal works. All right, so we can implement the display method using any of these traversal methods. Okay, and now finally let us take a look at the delete. Whenever we are trying to delete a node, there is going to be three methods. Three cases. Let us take a look at each of the cases one by one. So whenever we are trying to delete a node, it it is not going to have any children. So node, node, node with 0 children, node with 0 children, node with 1 child, and the last case is node with 2 children. Okay, so this is case 1, case 2, and case 3. So in case 1, let's say we want to delete a node. uh, let's say we want to delete this node, which is 11. So we can basically unlink the link from node 13. So now the tree is going to look like this. So 16, 13, 21, 11, 15, 19, and 26. So when we delete this 11 node, so we can get rid of that node. Now the binary search tree is going to look like this. So that's the deletion of a node with 0 children, since 11 did not have any children. So that's the case 1. Now let us take a look at the case 2. So let's say uh, we have this 11, and let's say it has a value 10. Okay, so let's say 10. So let's say we want to delete a node with one child. So let's say we want to delete 11. Okay, now we will go here and we will just store this parent reference to some temporary variable, and then we will delete this node and we will link this node to this 10. Okay, so that is how we delete a node with one child. And now we have to take care of this third case, node with two children. Okay, so let's say we have this binary search tree. So let's say we want to delete node 13. Okay, so what we are going to do is we are going to get rid of this node 13. And now as you can see, the binary search tree is not balanced, and it does not look like a binary search tree. What we need to do is we will take this node 15, because this node 15 is going to be less than this root node, and it is going to be greater than this node 11. Okay, so that's the perfect number to put it to substitute in case of the deleted node, because that value, which is 15, is going to be less than root node but greater than the left left child. Okay, left child of the deleted node. So here we can see this now satisfies the property of binary search tree, because the parent node should always be greater than left child, but less than right child. Okay, so since 15, this number 15 is less than 16, but it is going to be greater than this left child when we replace it with the deleted node. So here we can see the property has been satisfied. So that's the deletion of a node with two children. Okay. All right. So this was about the binary search tree. I hope you guys enjoyed this lecture video. I'll see you guys in the next one.